Good day everyone. Today, I'll be presenting on biological hazards, epidemics, and pandemics, with a specific focus on the COVID-19 outbreak and its impact in Selangor, Malaysia, using data from the year 2023. Let's explore how the virus spread and how we used mathematical modeling to understand the trend. COVID-19, first identified in 2019, has had a profound impact globally. In this presentation, we'll look at data from Selangor, Malaysia, focusing on the number of new COVID-19 cases reported over a 10-month period in 2023. Our goal is to analyze this data and identify the best mathematical curve to represent its trend. Before diving into the data, let's briefly understand what COVID-19 is. It's a contagious disease caused by the SARS-CoV-2 virus. It spreads mainly through respiratory droplets, and symptoms can range from mild to severe, including fever, fatigue, and breathing problems. While some recover quickly, others, especially older adults or those with existing health conditions, face severe complications. Based on the data obtained over a 10-month period in Selangor, COVID-19 cases showed noticeable monthly changes. Starting with 3,236 cases in the first month, cases surged significantly in the fourth and fifth months to 7,102 and 9,215 respectively, marking a major outbreak peak. Following this, case numbers sharply declined from the sixth month onward, fluctuating between about 1,000 and 4,266 cases. This decrease likely reflects effective control measures and behavioral changes among the public. Overall, the data reveals a clear pattern of rapid increases followed by steady declines, providing important insights into the outbreak's progression and prevention efforts. Now, let's look at the data. Over 10 months in Selangor, we observed significant fluctuations in COVID-19 case numbers. The year started with 3,236 cases, followed by a steep rise, peaking at 9,215 in the fifth month. After that, the number of new cases declined sharply, likely due to effective public health measures and behavioral changes in the community. This pattern, sharp rise followed by gradual decline, is common in epidemic curves. Before doing any work in Maple, we restart the session to clear previous variables, then load the linear algebra and plots packages which we'll use for matrix calculations and plotting. T represents the month numbers from January 1 to October 10. FT is the actual number of new COVID-19 cases in Selangor for each corresponding month. This is your output data, or Y values. DD equals point plot, T, FT, symbol equals circle, color equals blue, symbol size equals 20 display, DD. This command plots the original data points using blue circles. It's a basic scatter plot showing how cases change over time. You'll notice a rise to a peak around month 5 and then a decline. Now we build a matrix called A that helps us fit a quadratic model. The matrix has 3 columns. A column of 1s for the constant term C, the months x, and the square of the months x squared. Next, we combine matrix late with the column of actual case numbers, FT, to form an augmented matrix. We apply reduced row echelon form, or RREF, to this matrix to solve for the coefficients A, B, and C. This gives us a first estimate of our model. But we also use a more common method in statistics, the normal equations. This means we compute a transpose times A multiplied by X equals a transpose times B. We calculate a transpose times A, which is a square 3 by 3 matrix, and A transpose times B, which is a 3 by 1 matrix. Before solving this system, we check the determinant of A transpose times A. If the determinant is not 0, it means the matrix is invertible and we can find a unique solution. In our case, the determinant is 435,600, so we're good to go. By solving the system using RREF again, this time with A transpose times A and A transpose times B, we find our coefficients. C equals 1194.70, B equals 1648.805, A equals 167.75. So the final equation modeling our data is y equals 1194.70 plus 1648.805 x 167.75 x squared. We then graph this curve alongside our original data points. You can see that the curve follows the data quite well. It rises rapidly, peaks at month 5, and then drops off, just like the real case numbers did. Calculating the error to see how accurate our model is, we compare the actual cases FT with the predicted values from our equation. We compute the error for each month, and then find the Euclidean norm, which tells us the total amount of error across all data points. The result is about 6,753, which shows our model fits the data reasonably well. This project shows us how linear algebra and matrix methods can be used to model real-world phenomena like the spread of a virus. Using Maple, we were able to build, solve, and evaluate a model that describes how COVID-19 cases behaved in Selangor during 2023. It's a great example of how math is not just numbers, but a tool for understanding the world. Using linear algebra in Maple, we found a quadratic equation to show the COVID-19 cases in Selangor. Y is equal to 1194.70 plus 1648.805 times minus 167.75 x squared, where y is the total number of new cases and x is the number of month. We solved the equations with matrices. The main matrix has a determinant of 435,600, which means it can be solved properly. To see how good the model is, we calculated the total error between the real and predicted cases. The error is about 6,753. This number shows how close the model is to the actual data over the 10 months. All our data was sourced from Malaysia's official open data portal. Thank you for your attention.